Section 10.1, Trails, Paths, and Circuits. So this is a downside or part of graph theory, and this is looking at how to connect things. So the initial problem was we've got this river. How many bridges can we connect this to? Where are those bridges? And in this particular problem, can you walk around the town, starting and ending at the same location and crossing each of those bridges only one time? So it's an interesting question, and that's where graph theory comes from, is trying to figure out questions like that. And as we can see, there's quite a few different ways that we can try and represent this. Here is our very simplified version of that same map that we saw a moment ago. And for what it's worth, if you're curious about the Konigsberg question, the answer was no, you cannot. So let's start with a definition. We've got a walk. So here we've got adjacent vertices and edges that we're going to go along. And you'll notice we're going to write it vertex, edge, and so on. And do note we do have a trivial vertex, which is just itself. We generally don't worry about that. So a walk covers pretty much everything. A trail means we don't have a repeated edge. A path means we don't have a repeated vertex. A closed walk means we're going to start and end at the same vertex. A circuit is a closed walk, contains at least one edge and does not contain a repeated edge. And a simple circuit is a circuit that does not have any other repeated vertex except the first and the last. So here's a little table kind of summarizing what we are allowed to have and what we aren't allowed to have. So repeated edge, repeated vertex. Do we have to start and end at the same point? And do we have to contain at least one edge? All right, so we briefly saw that notation earlier, but we've got it down here as well. Now the nice thing about this notation is it's pretty unambiguous. It tells us I start here on edge 1, I then go edge 2, edge 4, and edge 3. Hopefully you can follow along there. We could also put it with the vertices. So we're starting vertex 1 to edge 1 to vertex 2 to edge 2 to vertex 3. I walk along edge 4, I've hit vertex 3 again. Here's edge 3 to vertex 2. And for this particular walk, there's where I'm ending. Now, with this one, though, if I wrote that V2, V3, that's a little ambiguous. Here, am I just going along edge 3, or am I going to go ahead and do this little circuit and then do it? I'm not entirely sure. So particularly for one like this, we might want to write out the vertices instead, or put vertex, edge, so on, just to again make it very clear where we're starting, where we're ending, and how we're getting there. So we've got a couple options here, and we would like to identify them as trails, paths, circuits, and simple circuits. So my first option, I'm going to go edge 1 on the bottom, to vertex 2 to edge 3. I'm then going to do vertex 3 to edge 4, so I'm going to take the little loop there. Then I'm going to go edge 5, and I'm going to end here at vertex 4. I do have a repeated vertex then, but I don't have a repeated edge. So we would say it is a trail, but it's not a path. Option B, I'm going to go edge 1, then edge 3, then edge 5, and then edge 5 again, so I'm going backwards, and then edge 6. Hopefully you can see my mouse there to follow along. And that is just a walk. It's not a trail. We had a repeated edge, and needless to say, we did have a repeated vertex there as well. All right, option C, I'm going to start here at V2, and then go to V3, so up this way. Then I'm going to go to V4 this way. Then I'm going to go to V5 down this way. Then I'm going to go up the diagonal to V3. Then I'm going to go down to V6. And then I'm going to come back up this way to V2. You'll notice we both started and ended at V2. We contained at least one edge, no repeated edges, so it is a circuit. However, we repeated vertex 3, so it's not a simple circuit. Option D, I'm going to go V2 to V3, to V4, to V5, to V6, to V2. So I went basically along that little house. And going there, it is definitely a walk. We start and end at V2. We've got at least one edge, no repeated edge, and no repeated vertex. So that is a simple circuit. Let's come back here, option E, I'm going to start on V1, then do edge 2 to V2, and then back along E1 to V1. So I'm just going back and forth along this bottom part here. And that is a closed walk because we started and ended at the same point, but it is not a circuit because I repeated edge 1. Last but not least, I'm just told V1. So here we're just at vertex 1. Now it is the first and the last, but it doesn't contain at least one edge. So it is not a circuit. We would just describe it as a closed walk. We could also describe it as a trail. So that'll hopefully give you a sense of this vocabulary and how to start reading all of these various graphs. So let's look at subgraphs. So a subgraph means that every vertex in H is also a vertex in G, every edge in H is also an edge in G, and every edge in H has the same endpoints as it has in G. So let's say we've got vertices 1 and 2, we've got edges 1, 2, and 3, and we've got the description of how they connect, and let's find subgraphs. So let's first draw that graph. So as you can see, we've got E3 is this little loop off V1, and then I've got my other edges connecting V1 and V2. We would actually have 11 subgraphs total, and I've got some diagrams here. You'll notice just the points. Anytime we've got just one edge, that loop, and then as we start connecting more. So you can hopefully see all of those pictures. And do note, the graph itself, the entirety, is also a subgraph of my graph. All right, let's talk about connectedness. Intuitively speaking, that means we can connect things without picking up our pencil from the paper. So everything is nice and adjacent. Our formal definition, we say two vertices V and W are connected if and only if there is a walk between those two. The general graph we say then is connected if and only if given any two vertices in the graph, there is a walk between them. And then there is symbolically that same statement. And if that is not the case, we would say it is not connected. So here are some graphs. Which of these graphs are connected and which of them are not? So I'm going to start here with A. Now you'll notice there's nothing connected here, but everything else is connected. We don't have anything just hanging off the side, so I would say that is connected. However, B and C are not connected. B actually has two parts and a point in between. So if you think about it, I can't get, for example, to vertex 4. Now, C might look connected because they cross, but V1 and V4 are connected, and V2 and V6 are connected, but there's no way to jump from this line to any of the other two lines. So even though they cross, they're not actually connected. There's no vertex in between. And you'll notice we could redraw that C graph like that, because again, we didn't have vertices there, and that might make it a little easier to see why that one is not connected. So here are some things to keep in mind. If the graph is connected, then any two distinct vertices can be connected by a path. If two vertices are part of a circuit and one edge is removed, then there still exists a trail between those two vertices. And if G is connected and G contains a circuit, then an edge of the circuit can be removed without disconnecting that graph. We can also talk about connected components. So we can say that if and only if H is a subgraph of G, H is connected, and no connected subgraph of G has H as a subgraph and contains vertices or edges that are not in H. So a lot of stuff to keep in mind there. So let's look at some components. So here's one big graph, and we would like to find all the connected components of that. So we are going to be able to write 3 of them. So for H1, we've got that listed here. Basically, that is this left-hand portion. H2 is this single point. V2 in the middle. There's no edges there, but that's okay. It's a single point. And then this right-hand side is H3. That is also a connected component, and we can see it listed there. All right, let's talk about Euler circuits. So we talked about Euler earlier. He was the guy who came up with that Königsberg bridge problem. So an Euler circuit, this is a circle that contains every vertex and edge. So in other words, it's a sequence of adjacent vertices and edges that has at least one edge, starts and ends at the same vertex, uses every vertex at least once, and uses every edge exactly once. So that means I can repeat a vertex, but I cannot repeat an edge. And our general theorem here is if a graph has an Euler circuit, then every vertex of the graph has positive, even degree. And we can say the contrapositive, if the vertex has an odd degree, then it does not have an Euler circuit. So let's keep that in mind and try to determine if this graph has an Euler circuit. So do I have any vertices which have an odd degree? Yes, I do. So here, vertex 1, there's 3 things coming off of it. It's got an odd degree. Vertex 4 has that one's even, but vertex 3 up here is often odd. So using that, I would say this graph does not have an Euler circuit. So again, if we've got even though, we are probably good to go. And if the graph is connected and the degree of every vertex is a positive even, then it should have an Euler circuit. Well, how do we find one? So here is my picture. How do I find that? So first, I'm going to look at every vertex and ask, do any of them have an odd degree? No, they don't. They do all have even degrees. So we should be able to come up with something. Now, there might be more than one way to do that. Here, I'm going to go ahead and start at A. So A to B, to C, to D, to A would be an Euler circuit. And that may not be the only one. So I had one little one here, but I can then draw a bigger one. So I am now going to look, I could go from D to E, to G, to H, to J, to I, and back to D. That's another circuit. You'll notice I could also combine these. Basically start here at D, go around this little box, and then go this direction all along this bigger box. So as we can see, there's at least a couple of them. And here's yet another one that we can come up with. So there might be more than one Euler circuit that we could draw given that same graph. And here is yet another one where now I am hitting everything. So here I'm going to go this direction. If you can follow, hopefully, where I've got here, I'm going to come up to F, back down across on 7, and then back down, and finally come up and hit D. And you can see the order in which we are hitting those to get around that full thing. So again, a graph G is an Euler circuit if and only if G is connected and every vertex of G has a positive even degree. We do also have a definition for a trail. We do not have any homework questions on that though, so I'm just going to pull that up so you can see the example, but we are not going to have to find that in the homework.